All right, so yeah, let's begin. Right. So open up terminal, wiggle it around to make sure that I'm recording my screen. And then I prepared some notes actually. So let me actually like drag those notes out. Okay. So yeah, what day is it? Yeah, so then I just wrote this recently. So okay, so some stuff main thing is, what does this even mean? Okay, so some stuff, what? Okay, so some stuff main thing as well, continue where left off from symmetries. Alright, sure, I'll take that. Basically, yeah, last time I was doing symmetry, so I'm just going to continue off of that. Let's just delete that. So here's basically like the to-do. Not for this stream, but like for like this stream and like for subsequent ones until it's like the to-do file, right? So we got to wrap up. So like we tested the horizontal last time for just like the symmetry state transformation. So you have to kind of finish that for the vertical and then the vertical and horizontal, or horizontal and vertical, the composite tests for game state transformations. And then I wrote like a thing which I have to test out, just a minor tweak to the game state print thing to replace like all these zeros clutter. Like if you look at like, maybe this one. Yeah, you see how like, all zeros or whatever? Instead of a bunch of zeros, maybe just like have it as like a blank space, right? So like the coins, like the ones pivot, like the ones, or like the health for the coin. Assume all coins will have full health, so like 1 out of 1 for now. No collisions between enemy coins or between coin and wall. So it's just all binary, 0 or 1. So instead of 0, we can just kind of make it as empty space so that just like the 1 stand out. And then the main thing for today is policy symmetries testing. And then I put some more kind of like ideas of like what to do in the future, which I mean, for now, like we just want to like do these two things. Like we're like wrapping up last stream's thing is like takes like let's get that done with quickly. And then that like does half of symmetries where we did the game state transformations. And then we have to test the policy. The policy is pretty simple. It's just a move ID, right? So it's not really a huge deal. It should be easy to test. But still, like these are like the two main ones. And then one thing I realized was, well, let's just go over these later. In fact, I just like wrote this bullet point. I just wrote these bullet points down recently. Like I'm not even like I may have to give these some more thought, but like I just like wrote down what was on my mind. I said make sure that we're calling GameState.refresh. Again, I did not check that. Then test conversion of policy to a vector and vector back into a policy. Parts of convert policy. Anyways, I'll go over this later. For now, let's just kind of like get started. So main thing is first, let's modify the print function. So yeah, let's just do that. We can quit this for now. Let's just full screen this and let's get started. Status, okay. So then yeah, get log just till I kind of, so like we kind of like fix the bug and apply move. And then where like we have to make sure to toggle the player's turn to the other player's turn, and symmetry.transformGameState, which is something by iteration, right? Like we realized we were doing one extra clone each time, so like one less clone. So that's good. So anyways, we were doing some stuff on Scratchpad, right? Let's just click that. Okay, so now wait, no, hold on. First things first, the game state, we're going to like hopefully improve this this thing here. Is greater than 0. Or else just instead of like 0, let's have it be blank, right? Just like that. So here's like a better view, right? Like you see like this whole like So like here's where we start off, right? Like this is our GS, it kind of looks like that. And then we launch this coin. Remember, this is GS next, this is GS next, and this is just GS. And then these are the three kind of similar things, except like flipped horizontally, right? So this is a much better visualization, actually. See how like these coins are like a nice starting position? Then we took this coin here and we launched it. Yeah, this is a great idea. I literally just had like very recently, whenever the note was edited. Like, yeah, just like before this stream, well, never mind. But like I just had this idea to like just print out blank space. Because I was too image stack focused. So anyway, so here's your kind of start. Then we take this coin here and we kind of launched it 45 degrees like this way. So it ends up here, like from here kind of goes here, which is, it ends up there. And then it's player two's turn. Player two is this side. Then player two's king, we just kind of decided to move it here. So from this one here, it kind of moves a bit like more, instead of like the outwards facing or like the arrow direction kind of changes, right? So like you can see like the kind of this thing. So now if you take this and you kind of mirror it like horizontally, so this one, like you kind of like look at that, then it's mirror, like if you see like this and that, then that's kind of like this stuff right here, right, is clearly like the mirror of like this stuff right here. Because like you see like this shape right here is kind of like that, but like they're both kind of pointing to this arrow sign is pointing towards the center like that. And like that, it's kind of like pointing to the outside, and like here it's kind of like pointing to the outside, right? Like, but yeah, so you can see how like this one is kind of like the same but flipped as that one, so that's like kind of visually you can see that. And here like you kind of have like this thing, and like the top left, like you see like these are kind of nice and even, but then here the top left is kind of like stretched above a bit. Like it's stretched a bit more towards this point right here. It's stretched a bit like away from every other coin. And its mirror right here, again, like these four are nice and fine, like this is fine, but this one like is a bit stretched out and away from all its friends, right? So like here the top left is kind of the odd one out of all the friends. I'm calling them all friends, but like it's kind of like the top left is the odd one out. And now here the top right is the odd one out. And then the wait, no, sorry. This one is not just this out, but this one out also. So like this one, sorry, I lost count. Like, yeah, my bad. But like this one is kind of like you have like this odd one out and like that odd one out too, right? But like here, this is the only odd one out. You have to skip by 3. So like skip 1, skip 2, then skip 3. Wait, what? No, sorry. Wait. Hold on. Yeah, no, it is the third one. So it's like GS NN, like next, then GS. Then GS NN symmetry, GS N symmetry, and GS the same raw GS object that's like equals, where like the bottom true or something maybe. But yeah, here only this one's the odd one out. Just like only there, that one's the only odd one out. Right? Like basically, like if you have something in like these top 3, then to get its pair, you'd have to add the period, which is 3. So like this one's symmetry is like 1, 2, and then this one would be symmetry. And the one below it would be like 1, 2, and then 3. This one's symmetry. And then this one is the exact same object as this one, so it's no wonder that they have the same output. Okay. In fact, get status, get diff, get add all. In fact, I'm just gonna commit this itself. This is like worth it's a very simple change, but it's kind of worth a commit. Get commit, modify, print. Wait, what was the function called? Modify or improve to highlight. Yeah, just improve that. to better visualize coin locations. Like we're basically decreasing the clutter in that commit. Status. Okay, great. So now we have handled we've handled this one, right? So that's excellent. We've just handled that one. And now let us continue with the testing of the symmetries. This should be like just take like a minute or so, or well maybe that's an exaggeration, but scratchpad.ts and then what symmetries.ts or symmetry.ts. So now like you see how like we have like this thing right here as a symmetry, like this. Now we have to test vertically, right? Vertically. So this is 0, like the symmetries of 0's identity. 1 is flipped horizontally, and now 2 is flipped vertically. So we have to do symmetries of 2, right? Wait, why did I quit? Sorry about that. Just like that, see? Symmetries of 2, right? And then next horizontal is now vertical. Actually, instead of horizontal, let's actually replace horizontal. Okay. Horizontal would transform. Transformed and then confirm. So next transformed. Actually, no, sorry, let's just undo that. Let's undo everything. And now let's just make this symmetries of 2, okay? I know it says flipped, sorry. Yeah, I know it says flipped horizontal, but let's just, or wait, no. Let's see. Okay. So next, and now it's just transformed. Transform, the next. GameState transformed. Next, transformed. Transformed. Okay, I think that's good. So we have, so again, like this stuff we've already seen, right? Where we basically have a GS, then we apply move 1 to get GS next, and we apply move 2 to get GS next. I think there's like a whiteboard for that, right? Wait, let's close this nonsense. No, it's like 1 minute left. Oh no, my board's hostage. Yeah, so like this is GS, that's GS next, and this is GS next. So it's initially like kind of like that, then this one's the odd one out, and this one stays odd, but then this king coin kind of migrates to center. So like the direction of the arrow from pointing outwards points inwards, or towards the center. And then, okay, great. So now, yes, so now like this is all standard. We've seen this a lot last stream. Now we have a symmetry. Instead of like specifying like horizontal or vertical, I'm just calling it symmetry and transform. I'm trying to like delete the word horizontal to make it more general. And we can just change this number to 3 and then maybe 0 for good measure, and then we'll be done with testing the game states, and then time for policy. So okay, so now next transformed. So this is a transformed game state where we just do that, and then we just kind of like print. We print the non-transformed ones, like we print like the top 3, except we're printing it out like this one, then this one, then this one, and we print out the transformed ones. Again, this time it's vertical. So I see nothing wrong with this. So I think we can just quit everything and then compile everything. And then let's do a little bit of a quick clear, and then let's do a node, run it. Okay, So now let's have a look. This is this thing right here is GS next, which is indeed looks like that, right? You can kind of see these two wave fronts or whatever. They kind of match. And then this one is like that one, except we didn't move the king one. P2 is king, right? So this one, again, looks like that. Checks out. Very good. Then the original game state just looks like that, right? And now let's consider this, right? If you flip this one vertically, right, instead of horizontal, if you make it vertical, then like, basically, well, we can visually see it, right? Like, yeah, let's just select. Let's just do a bunch of deletions. Take all these things and let us delete them, right? Let's just delete them. In fact, let's delete all these things too. Okay, so now let's just kind of like look. Well, if you flip this one vertically, then how do they look if you do a vertical flip, right? So then when you flip them vertically, then this one would like, these would basically be kind of like the same, I think. But then these ones would like be like this odd one out, which is in the top left, becomes still in the left, but now the bottom left, right? So like this one is the odd one out, and this one. And yes, this one is still kind of odd, but like these two are kind of odd. But like in terms of like the change, I don't think there's a change, right? Is there a change? Because it should be in the middle, right? Anyways, well, let's just have a look, right? So now like these things right here, right? They basically kind of look the same as that, like visually, like that kind of looks the same, like tick, 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 just like tick, 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 right? Like tick, tick, tick. But now we have like tick, tick, but then tick, right? Like tick, tick, tick. like this tick, 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 and like tick, tick, but then tick, right? Like what I'm saying is like this and this are kind of like similar, but then a little bit of a difference where that one's the odd one out, right? Just like now, like this one, same, similar, but this one is odd. So like rather than like, yeah, so you can kind of see how like this one and this one are like vertically flipped complements of each other, right? And then, and now let's consider this. Same thing, like where these are going to be the same, but again, this one's going to be like the odd one out. Like, so now let's compare this with a 1, 2, 3, right? So like these three right here still match those three, right? These three match those three. But then this one, same exact thing. This odd one is in the top left, but now the odd one out is this one right here, and it's in the bottom left, right? So like if you look at that right here, and you kind of like take this and you kind of flip it vertically, again, these things should basically kind of, if you flip it like vertically, then this should kind of like look the same. And these two would kind of like go here and here. Like these two become these two, and then this odd one out becomes this odd one out, right? Same as we saw there, right? Like that. Only difference is like kind of like these two, right? Because of the move two. But anyways, like if you just kind of like compare. If you kind of compare this one, like right there, that's this one right here, right? And then the original one, same thing, right? Same exact object. False true. So what are these false truths again? So false because should point to a clone. Yes, there should be different objects. That means like this object here and this object here are two different objects. That is correct. But then both of these, their previous ones, should actually be the same one. Like, yes, these are two different objects, but then these both, like this is a back pointer to here, and this one is a back pointer to there too. So like these two previews should be the same. So that is true. And then this one, I mean, obviously, like, if you take this one, you go back, you hit GS. And if you take this one back, I mean, that's by definition, right? GS, obviously. So yeah, in fact, the last one seems a bit stupid. But anyways, that's in fact, let's just delete those. Let's just delete those statements. Okay. Now let's test the composite symmetry, which is symmetries of 3, which is horizontal and vertical. In fact, before we test them, let's actually like draw them out, right? Let's just draw them out first, right? What? Okay, so now horizontal and whatever, let's ignore it. Probably still sent it. Anyways, so horizontal and vertical, that's a bit of a tricky one. So then let's consider these two. Horizontal and vertical, they should still basically like kind of more or less stay the same. And this one horizontally flipped ends up, wait, what? This one horizontally flipped like stays the same, but then vertical kind of puts it up there. So then like, so these two we've done, and this would end up being, I think, like this. And then like this one here would kind of go like that. And then this one would go down here, and then flipped would go there. And then wait, so this one would go there. This one, these two would go there, and then this one here would go down here and then there. Ah, but no, this one is wrong. This one should be here, and this one should be here. Oh, let's just wait, what? Sorry about that. So then this one kind of becomes here, and this one kind of goes there. So here's what I expect. Something that looks like this, where this one is the odd one out. And like these are the kind of like, and the general shape looks like this. That's kind of like the shape that we see. And then for this one, what I would expect to be is, okay, so these three here would kind of become those three, so these three there become that. And then this one right here would basically kind of stay the same. And this one right here would kind of go here and then go here. So basically these two become these two. But then this one right here, so first goes like a bit here, and then it kind of goes down, right? Just like it did there. So like now the shape is kind of like this, but then like that. So like this kind of curve is the same in both, but then like this one kind of becomes that. And this one is the original. There is no change there because that's like same thing, right? Yeah, thinking of them in terms of curves is kind of, I think, a nice nifty idea. Now we have just got to compile it. Let's do a clear and then let's run it. Okay, so the first three, we've seen them so many times, right? This, nothing different. Now let's look at this, right? This is this one. This is the next flipped. This and longer, right? Like this and longer, good. Now this thing, the right-hand curve is the same, but then this one kind of flips like that, like you have like this and like that, which is this and like that, and then this one is the same object original. Okay, good. Get status, get diff, get add all, get status. Okay, great. So I think now we've basically wrapped up this thing. I said it should be fast, but I'm already a bit Petard. Okay. Now what we have to do is test policy symmetries. But I think for now, I mean, kind of want to just call it a stream right now. It's super short. Let me think. Policy symmetries testing. Policy symmetries testing. 4:32. A new LeetCode comes out at 5 o'clock. If I just do some work on this one and then do a LeetCode maybe. Actually, I'm a bit bored. Maybe I'll just do some LeetCode. I'll do a quick LeetCode question. Already solved this from last year. Pick a random one. Submissions, no data. Oh yeah, it's a 3K plus one, 3047. Okay, let's look at the like-dislike ratio. Okay, so about double the likes. This is lots of dislikes. What's the percentage acceptance? Oh wait, no, that's the new version that has a percentage. Percentage 44%. Okay, maybe it's worth doing. There exists n, well, not enough numbers for like this. Okay, there exists n rectangles in a 2D plane. Okay, nice, it's visual, and I'm just kind of like doing whiteboard visual stuff too, so I guess that could be a nice coincidence, or might be a nice thing. Well, let's see. There exist n rectangles in a 2D plane. You're given two zero-index 2D integer arrays, bottom left and top right, both of size n by 2. You're given, there exist n rectangles in a 2D plane. Okay, n rectangles, how many rectangles? N. You're given two zero-index 2D integer arrays. So two arrays that are just 2D, bottom left and top right, both of size n by 2, where bottom left of I and top right of I represent the bottom left and top right coordinates of the ith rectangle. Okay, so basically, like for let's say I equals from 0 to n minus 1, presumably, then like the ith number, like bottom left of I gives you the bottom left dot here, and then this would be top right. So basically bottom left of I and top right of I, like together, they specify the entirety of the ith rectangle. Okay, good. Represent, I just read this. Represent the bottom left and top right coordinates of the ith rectangle respectively. Yeah, that's what, yeah, okay. Yeah, that checks out. You can select a region formed from the intersection. This is some interval crop. You can select a region formed from the intersection of two of the given rectangles. You need to find the largest area of a square that can fit inside this region. If you select the region optimally, return the largest possible area of a square, or 0, if there do not exist any intersecting regions between the rectangles. So bottom left is 1, 1, and top right is 3, 3. Okay. And then you have 2, 2 here, and 4, 4 here. And then we have 3, 1, 3, 1, 3, 1 here, and 6, 6 there. And then 1. because if we draw it out, then we see that these two kind of have that. Okay, that's fair enough. And then here, just kind of visually, like, we can assume that, like, these things, like, kind of visually is again, like, yes, we have, like, 1 by 2 and 2 by 1 rectangles, but we need it to be square. So again, it's there, and then this one's 0, because nothing actually intersects. Okay, so then one thing that kind of, like, jumps to mind purely visually, and from doing many interval, not many, but quite a few interval questions, is presumably we're going to sort things on the start point, right? Or like on the x's, like kind of like going from this way to this way, like the bottom left, from the bottom left coordinates, right? We can kind of like sort them based on like the x's, right? Maybe like that. So you have like this, then this, then this, because it's like 1 and 2, then 3 for like the bottom left of 0. The first, like n by 2, right? It's like bottom left of I of 0. Like that's like the 0th one of like the first thing in this pair of bottom left could be like the x coordinate of the bottom left. We can sort on that maybe. That could be a first step. And then what? Like, and once we do that, then what's the idea? So like if we were to kind of visualize this as a 1D problem, right? It would just be intersection of intervals, right? Like instead of like 2D, if it were just kind of like this, 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 and this, then you want like the longest intersection. That would kind of be like this, like that would be kind of like your intersection, like this one and like this one, right? So like that's like the 1D version, I guess, this intersection of intervals, and find like the most overlap. But then the only difference now is like we're making it like 2D. So like even if like you have like an intersection here, like what if like it looks like this in the 2D case, and like even though like the x's have something, the y side does not have something, right? So like it adds like a bit of a wrinkle, right? So maybe like what if we kind of like, so like, okay, let's just say like forget this problem. What if like we have like just 2 boxes, right? Then how do we find out the area of the intersection? Like how do we find the h and the w? And then given h and w, how do we find out like the square? It would just be like min of h of in h comma w, and like this whole thing would just be squared. Or maybe I can like do like min squared of like h comma w, right? This whole thing squared, like kind of like that. So like given like this coordinates here and here, like we kind of we can get like the w, sure. Like if you have like just like this in this for just 1D case, then like this is like S1, E1, and like S2, E2. And if we've already sorted on the starts, that means we know that S2 is greater than like, let's pretend everything's strictly and there's no equality here. Then as long as S2 is strictly less than E1, we know that there's some overlap. So like this thing right here is going to be E1 minus S2. That will be its length. And what about the height? Here to here and then there to there. So then okay, so the naive solution, which just jumps to mind right now, just being completely naive, is what we can do is we can like compute every single pair. So if you have n rectangles, then we would have like O of n squared pairs. And then for each pair, what we do is like we do this kind of computation, which will take constant time. So it's an n squared solution. And this clearly n squared just feels very wrong, right? I know we have to do sorting. It's just Because like in the 1D case, I know we do sort, like just greedy. Like we just kind of sort and then we go from left to right, right? Like that's kind of like the thing. So then, what if like we do like, okay, so then, okay, what's n? Like what is the size? The bounds, right? The bounds are n from 10 cubed. Oh, 10 cubed is a really small number. N squared is just a million then, right? Like 1,000 squared, worst case. Now I feel like sorting is important. Okay, so in the 1D case, what we do is we sort by like the start points. And then like, so like we have like a start point here, a start point here, a start point here, whatever. So then first we have this one right here. And then we have this one. So first we see this one, then we see this one. And like, since the start and the end, so then like we get like, this is the possible overlap. And then we see this one here. Oh, we should also keep track of the minimum ends, right? Like this is the minimum end. So as long as this start is like kind of here in the minimum end, then like we kind of compute that overlap. But then the moment we see a start that's after this minimum end, like this one, then like this one can never be considered anymore ever again. So then like the next minimum end is like, let's say this one was a bit longer here and so forth, right? So like there could be some kind of like, we could keep track of like the minimum ends as well, maybe. Like a heap of minimum endpoints, or does it have to be a heap? I mean, I know we incurred like, by sorting we have like n log n already, so heap's probably okay, but I don't know. Anyways, the point is that like we sort by starts, and then like when we're adding in new segments, then we have to like kind of consider like the end. So we have this one here. Let's like start fresh. So we have this line here, sure. And then we have this one here. And then we'll have like this one here. And now we'll see a new line right here. So like, and because this one is kind of like after this one, the minimum end, then we know that this one will never be considered for all future overlaps. So like its reign is done. So maybe we sort by endpoint, right? Instead of start point. What if we start by the end? No, start just seems visually correct to me, or it makes sense to me. Maybe they both could work, but so like we're here and then here and then here, and then because of that, so like here and here we get this overlap, then here and here we get that overlap, and then this one has to be kind of removed from consideration. And then so here we have like, this is the endpoint and this is the new minimum end. And this one here. And then now once we kind of go here, then we can kind of remove this one from consideration. And then the new minimum end is this one. So then we kind of like match on that. Okay, yeah, I think we have a heap of the minimum endpoints. That could work, a min heap on that. So like when we see this one, then like we look at the heap of the min endpoints and this one's the least, so we remove it. And then the next one, well, this one's inside it, so we compute that match. So that is one way of doing it for the 1D case. I think I have a solution, like sort by start, like sort start ascending. In fact, there's a question called meeting rooms, I think, and I think like this is kind of ASC, not ACS, ascending, and then min heap on end. Min heap on end. Or actually, maybe there's a way without the min heap if we sort by ends. Maybe, I'm not sure. Anyways, but we know this is still n log n. I may think about, but anyways, the point is that like I know I can solve the 1D case. So now let's consider like kind of generalizing it to a 2D case. So now let's kind of like say that like we have, so like now we have like the start, but then we have like this. Then we have another one here, which is like later start, like this start, and this one is like, this one's to the right, right? Its leftmost is to the right. But then like there's no y version. So like the y and the x are kind of like independent of each other, right? So like okay, let's consider like the same example case, but let's kind of like make it 2D. So here we have like something, and then we see this one, which could be like, it could be here, it could be up here, could be down here or whatever. So then like we could kind of like see something like that. Let's pretend that it's here for whatever reason. So then we kind of get a square, which is like the square sum. We get some kind of test of the answer. And then we'll kind of see this one where it could be like out of bound, or maybe it could be like, just for some more interesting thing, could be like that or whatever. But how do we test like, how do we test the y's though? Like sure, like if it were just x, if it were just like 1D, we could do it in n log n, right? Just n log n pretty easily by using sort by greedy, and sweep from left to right as n log n if it's 1D. But then the problem is like when testing against y's, doesn't it kind of like doesn't this like kind of fundamentally become a 2D problem then? Like, because the y is independent of x, so like, so then we can like sort by 2 keys, like the x's, and then sort by like the y's as well. No, but they're independent of each other. Okay, 4:50. It's almost 5 o'clock, so I'm spending too much time on this question. Kind of want to click the hints. Okay, let's look at this square. Then we see this one. So like we know that like there's like, because this 2 is less than 3, like we know that like there's like a unit 1 overlap in the x component. But then again, this thing could be translated somewhere else. So like we'd have to like kind of compute its y. So basically like we have some heap of like the min endpoints, like the ending points, the min heap on endpoints. And then when we see a new rectangle, like we have like some stuff, some rectangles already there. Like we have like this rectangle here from like this X. We have this one, and then we're gonna add a new rectangle, right? Like this one could be like here, and this one could be like here, whatever. And then we're about to add a new rectangle, which kind of has like the X's kind of locked from here to here. Like it could be this, could be that, could be this, whatever. But the thing is that like we know that like this start right here is less, or is this start like right here is within both these endpoints, right? So it could like we have like a heap of like order n size, but then when we add this new one, we'd have to test against like the entire heap, right? Like it could potentially be anywhere in this heap. So this thing, like this one thing here that we're testing on, we're testing on order n of these things. And for each kind of new interval, like new rectangle we add, we're gonna have to test against like every single thing in the heap, right? And there could be order n of them. So isn't that like n squared? Or is there some like amortization or something? Because like, let's say that like this one, we kind of tested against these two and it kind of looks like this. Then you get some sliver, but then in the future, like we might see something like this, which kind of like still fits between them, but then like it's like super like, but because of the heights, like it's a bit different. Oh no, but we can't do that because it's a min. It's a min. The crucial component is a min. So like whatever kind of like, wait, maybe there is a trick, because like whatever this thing is, like if it intersects with like this one, or like whatever like the best one you get, like for this one, right? For this square right here, or this rectangle, whatever we're intersecting on, which is the best, would be like against this one, right? Where like this thing right here, and then like would be kind of like capped by the square would be capped by something like that. Wait, no, but what if the limiting factor is the y dimension, not the x one? Then future one could kind of come in with a better y dimension. So because of that, we can't really like say that, hey, like we tested it and we can remove it from consideration for the future. Like this notion of removing from consideration for the future is where the optimization, the amortization comes into play. But I don't think we can do that. So maybe it's just pairwise, right? We just test all pairs of pairwise of the rectangles. And we just do the formula, right? Or the min of whatever, like the min of the x and the y direction, just kind of test them, right? Let's click hint. I think that's the answer, but hint. Brute force, exactly. It's a brute force. It's pairwise. It is n squared of each thing. That's it. Because like, yeah, like 10 to the cubed, like just 1 million, right? So yeah, I guess it is n squared. That's kind of unfortunate. I was hoping for a bit better, but anyways, I was wasting lots of time. In fact, yeah, okay, let's just quickly do this. Try to finish it before 5 o'clock next. Actually, let's just, yeah, LeetCode problem set all. I prefer LeetCode to BumperCoins right now, to be honest. Okay, so yeah, in just 4 minutes and whatever. Let's just see if I can write this on time. It's n equals bottom left dot length for int I equals 0. I is less than n. I plus plus. For int j, or j equals, so we test each pair, so then j equals to I plus 1, and then j is less than n, j plus plus, test rect I overlap rect of j. Okay, so to test the overlap of the so then int overlap x equals what? The overlap of an interval from the x dimension. Like if you have like this and this, right? S1 and then like S2 or and then E1, E2. Yeah, it took me a whole bunch of thinking before I realized that it's going to be n squared no matter what. So it's brute force pairwise. But when I say pairwise, I mean like every possible pair, which is brute force. So let me refresh. So then for an interval S1, E1, S2, E2. Okay, so then first we have to check, like, let's say, like, how do we know if this interval actually overlaps, right? Then let's so S2 has to be less than E1. Has to be less than E of 1, right? Like the start has to be less than the end of the other one. Like this start is less than the end of that. This start is less than the end of that. Like that's the thing, right? And S1 is less than E2. Is that the overlap test? Like, could there be like some counter argument? Like, if they don't overlap, then like you have like S1, E1, and S2, E2. So like you have like, so then E1, so S2, so like this thing would be false because S2 is not less than E1, but then this one would still be true. So I think like we need both of these starts to kind of, I think like this is the expression, right? So if bottom left 450, okay, maybe I'm not gonna finish it. Or long min wait, hold on. Okay, do you have to enter your room? Can you wait for like 5 minutes? Or maybe 10? Well, right now it's bad. What? All right, I'm just gonna have to quickly finish this. Or actually, hold on. Unfortunately, it looks like I have to briefly move rooms. All right, let's brighten the screen a bit, and then let's just finish this. So okay, so then min equals or long dot min value, and then or sorry max. Return max, right? So then if the what? The bottom, so if the bottom left of I of 0. So then we have like if the start is less than the end of the other one. So I'm just gonna use like, I'll use like this red one and this blue one for reference. So this is the bottom left of the like, this will be I and that will be J. So then like if bottom left 0 is less than what? This one has to be less than this one, right? So this one here is going to be top right of J of 0, right? Coordinates three, 2, 2, 1, 3, 4. This point here. So I'm assuming like it's x comma y, right? Like the coordinates are in the form x comma y, I think. So then like, so bottom left of I of 0, and then top right of J of 0 to get the x1. So like this is less than this. And then kind of the other way, where it's like we take this whole thing here, but then we kind of flip the, we do a bit of a flip somewhere, where like the bottom left of the J of 0 would be, I'm guessing, top right of I of 0, right? So this one is a top right I of 0. So if that holds, then int or long overlap x equals 0, long overlap y equals 0, overlap x equals to what? Well, we basically like the overlap is like this thing right here, right? So the overlap basically is the max of the starts, right? The max of the starts and the min of the ends, right? The max of the starts and then the min of the ends. So that's the max of the starts and the min of the ends. So math.min of the ends, which are the ends are actually, this is quite a helper function, which does the whole interval stuff for us. Private long get overlap of int or long s1 long e1 long s2 long e2. And let's have a convention that return -1 if no overlap. Then let's just use a helper function. I think that would be a better idea. So if s1 is less than what? S1 is less than E2. It's less than E2 and just delete everything. And S2 is less than E1, right? And S2 is less than E1. Else return -1. Return math.min of E1, E2 minus math.max of S1, S2, like that, right? So I think that is your overlap. So then long overlap of x would be get overlap of, what is S1? Bottom left of I of 0, and then E1 is top right of I of 0, and then S2 E2. So S2 would be bottom left of J of 0, and then E2 would be top right of J of 0, so just replacing the I's with the J's. And then if overlap x is less than 0, is less than or equal to 0, continue. Overlap y equals get overlap of so now we have like this and this, right? So then here it would be, what is this point, like what is the y for this one? It would be still bottom left of, let's just take this whole thing here and just kind of like that. But then now instead of like zeros, we just replace them to ones, right? So like bottom left of I of 1, and this top one would be top right of I of 1, and presumably the exact same thing for the j, right? 1 and of 1, and then same thing here, where it's like kind of like that. Overlap of y is less than 0. Then long edge equals math.min of overlap of x and overlap of y. Then max equals math.max of the max and the edge times the edge, which is the area of the square, right? Just like that. Test it out. Runtime error. Edge. Okay, so test case 1 works. Let's try test case 2. It works. Test case 3. Error. Okay, good. Turn max. Oh, I think max is greater than 0 max, or else 0. Cause like some negative nonsense. Cause like here, like reset test cases. Basically, like at the end, if there's no overlap, then we're kind of left with a very negative number, but then we have to kind of make that 0, something like that. So try submitting. Only beats 12%. It only beats 12% of solutions. Okay, that's kind of a bad performance. Let's just click solutions here. Yeah, I think we're gonna have to basically brute force it, right? overlap. Okay, whatever, that's pretty unstimulating. So now we should have a new LeetCode question. When I click refresh, this should change. And it is an easy question. I'm not gonna do easy. So I'll just end it right now. But yeah, I guess the only thing we did really today was we just finished the symmetry testing for the horizontal, I mean the vertical, like all the remaining symmetries. Well, we didn't test it for a clone. Yeah, let's just quickly test it for the identity symmetry too. Let's just test it for identity symmetry and make sure everything is like, it looks exact same. Cause like if you look at like symmetry, and like you look at symmetry of 0, that's the identity, right? So it's just like a no operation, it just clones everything. So let's just like kind of verify that all the images look exactly the same. Boom. So here we have like this one here, and then it matches. So then like 1, 2, and then 3. So you have like this thing, like you have like 1 here, and then like 1 small one, and 1 where this one's odd. Small one, this one's odd. Then we have the same, this one is odd, but then like this one kind of swaps directions. So then from here we go 1, 2, 3, where like this one is here, which matches that, and this one here matches that. Final one is the initial one right here, and that's this one right here. So basically like these are all the exact same. So that's a good visual confirmation. So we're basically done with symmetries, and then we changed the print helper function to basically store like show like blanks and only like write stuff out if it's a coin there basically. So like this way we can like basically like see the contours. We can see the locations of the coins visually. It's a very minor change, but like it really helps debugging, I feel. So yeah, we basically verified symmetries, and then next time we're going to do policies. But yeah, I guess I got too caught up into like kind of intervals when it comes to like 2D, because like, well, never mind. I got a bit tripped up on that question, or I spent too much time on it. But anyways, yeah, let's look at the topics. Yeah, very, very simple. Like there's no like greedy, like there's no like priority queue or no sorting. It's just a very boring question actually. Anyways, I'll just end it here.